Hey guys, welcome back, and today we're going to be going over 7.1, which is basic trigonometric identities. And for the think/warm-up, I have what do you get when you use the Pythagorean theorem on the unit circle. And here, remember that we used to have x and y here on our unit circle, and this point was also x and y. But we know from our unit circle back in chapter 5 that x is really just cosine of theta and y is really just sine of theta. So I have that used there. So I want to use cosine and sine instead of x and y when I'm doing the Pythagorean theorem. So I'm going to get one side squared, which is cosine squared theta, plus the other side squared, which is sine squared theta, and then equals the hypotenuse, which is just 1 squared, which if I were to simplify this, I might just write sine on this side, sine squared theta, just because we usually see sine first, not for any particular reason, but sine is just usually what we do first, and then 1 squared is just 1. And this is one of our very important trigonometric identities that we're going to talk about later on. It doesn't have to make much sense right now, but know that this is where it comes from. It comes from doing the Pythagorean theorem on this unit circle. So a statement between two expressions that is true for all values of the variables for which expressions are defined is called an identity. So for example, x squared plus y squared, this should be minus y squared actually. X squared minus y squared. This is what it should say. X squared minus y squared equals x minus y squared times x plus y squared is an algebraic identity because it is true for any numbers you put in for x and y. That should say in. A lot of typos on this one. But in for x and y. So this should be minus, and this should say in. In for x and y, right? No matter what values I put in for x and y, this statement is going to be true. So an identity involving trig expressions is called a trigonometric identity. So the equation, for example, the equation we just found in our think/warm-up is a trig identity because no matter what angle I put in for theta, this is going to be true no matter what, right? If I put in 30 degrees, 60 degrees, 47 degrees, this is going to be true. If you find a variable for a variable that makes an equation false, then you have produced a counterexample. And it only takes one counterexample to prove that an equation is not an identity, right? If you're saying something works for everything and you find one thing for which it doesn't work, then you haven't produced an identity. So for example 1, we have prove that sine x and sine x times cosine x equals tangent x is not a trig identity by producing a counterexample. Now, when I'm doing these, there's multiple ways to go about these. I'm going to try and think with some foresight, and I'm trying to think where can things go wrong. And in a mathematician's head, thinking with foresight, I'm thinking, hey, tangent of x is undefined in some places, right? Remember our graph and how we have those asymptotes? Sine and cosine doesn't have that. So remember, one of those asymptotes is at pi halves. So maybe if I plug in pi halves for my angle, something weird will happen. So if I put pi halves in, I'm going to get sine of pi halves times cosine of pi halves equals tangent of pi halves. And we're asking, is this true? And so sine of pi halves, if we think about our graph, that's 2 pi, halfway is pi. This is pi halves. This is why I think the graphs are really important. Or you could use your unit circle. So a pi half sine is 1. For cosine, we have it like that. 2 pi, in the middle is pi, and then here is our pi halves tick. So I like to think of these graphs in my head once you're comfortable with them, but if you need to sketch them out, by all means go ahead. And so we know cosine is 0 at pi halves. And then tangent to pi halves we know is undefined. That's also from thinking about the graph. Well, and this is just simply not true. 0 does not equal undefined, right? 0 does not equal undefined. 0 equals 0, right? So this is one counterexample, and that's all you need to prove the statement false. Now, without foresight, you could also just plug things in and see if it doesn't work, right? Which there's a lot of values for this for which it wouldn't work. Sometimes, for identities or for equations, you'll only have one value that doesn't work. So you kind of have to use foresight, but this one, there's a lot of inconsistencies. So for example, let's just do, just to show you that there's other ways. Again, once you've found one, that's all you need. So you would be done here. But I'll show you the example the book does. The book says, hey, plug in pi fourths, so then you get sine of pi fourths times cosine of pi fourths equals tangent of pi fourths. And you could use whatever method to determine what these are. Pi fourths is 45 degrees, so you could probably use your 45, 45, 90. I know at this point that that is the square root 2 over 2. This is also the square root 2 over 2. Or sine of 45 degrees or pi fourths is square root 2 over 2. Cosine of 45 degrees or cosine of pi fourths is also square root 2 over 2. And I know that tangent of pi fourths, if I were to look at my graph, is 1. That's the 1 we know from there. Or from the unit circle, you could find these, or really anything, right? Square root 2 times 2 is, or square root 2 times square root of 2 is 2. 2 times 2 is 4. And remember, this was a question. Does this equal this? And then we get 1/2 equals 1, which is simply not true, right? So there's another counterexample. But again, you only need one. But if you found either of these or any other one, then you would be good. So here are the identities for the entire chapter that we're going to talk about. So remember how I said sine squared plus cosine squared equals 1 was an identity? These are all the other identities, and I'm going to post this on Google Classroom. This is for the entire chapter, not just this section. So I have all of them right here. You can either write them all down right now, or you can print off the sheet. I would almost recommend doing it on a page totally by itself so that you can reference it on your own time while you're working with them. And I've pre-written the brackets on the ones in this section. So these are the ones we already know, right? Sine is a reciprocal of cosecant and vice versa. Cosine goes with secant, tangent goes with cotangent. They're reciprocals of each other. Those are the ones we know. Those are just by definition. These quotient identities, we've seen this one before, maybe in passing. This tangent of theta equaling sine theta over cosine theta, that comes from our unit circle, because tangent of theta was y over x, and y is sine and x is cosine, so that's where that comes from. And then cotangent is just the reciprocal of tangent, so we just flip those around. These are a very important one as well. And then the other ones that are in 7.1 are sorry, let me underline that, are these ones. All right, we have sine squared plus cosine squared equals 1. That's the one that we found. And then simply by substituting some things in for sine and cosine, we can get these other two, which are also going to be important, and those are called the Pythagorean identities. These other ones are used later on, but you are welcome to write them down now. So I'm going to scroll through them, and you could pause the video and write them down if you wish. If you'd rather just print off what's on the website or what's on Google Classroom, or just write it down later, fine by me. But I'm just going to do a quick scroll through, and if you want to pause and write them down, you absolutely can. This is where we would be heading for the rest of the unit. Some of it looks scary, but don't worry. You take it on one at a time. But again, oh, these ones too. These ones are in 7.1 as well. Should have mentioned that. Okay, so use the given information to find the trig value. We've kind of done these before, but we're going to do them a different way now. So if I have secant of theta equals 3/2, find cosine of theta. Well, I want something that's going to involve secant and cosine. Luckily, I already know that cosine of theta is 1 over the secant of theta. Right? There's something that involves both of those. That's this identity here that we already knew, right? And hey, it says right there that secant of theta is 3/2. Multiplying or dividing by a fraction is the same thing as multiplying by the reciprocal, so we're going to get 1 times 2/3, or just 2/3. And there's our answer for that one. This one takes a little more foresight, but it's totally doable. So I want to find two things. I want to find something that involves cosecant and tangent. So I have cosecant, and now I'm finding tangent. So cosecant and tangent don't go together as reciprocals, so that's not going to be it. I don't see cosecant and tangent together here in any way. I don't see either of them here. I see tangent here, but I don't see cosecant. I see cosecant here. Oh, but here's cotangent, right? That's not tangent straight up, but we know that cotangent goes hand in hand with tangent, so maybe I could use this one. So that's like my thinking process, right? I'm going like down the list to see what I could use for this to work. And so that's why I said it might be beneficial to have it out separately. So I'm going to use this identity right here, 1 plus cotangent squared theta equals cosecant squared theta. I'm just going to flip it the other way around. I'm going to say cosecant squared theta equals 1 plus cotangent squared theta. All I've done here is rewrite that identity, right? Well, I have cosecant of theta equals 4/3. So cosecant of theta squared should just be 4/3 squared, right? Little mini lesson here. When we say this, that's the same thing as squaring the whole thing. And then equals 1 plus cotangent squared of theta. Well, 4/3 squared is going to be 16/9 equals 1 plus cotangent squared of theta. If we subtract 1 over, subtracting 1 is really going to be like subtracting 9 over 9, right? 9 divided by 9 is 1. So 16 minus 9 is 7, and then we're still over 9 equals cotangent squared theta. Take the square root, take the square root. Whenever we take the square root, we have plus or minus. So then I get plus or minus the square root of 7 all over the square root of 9 is 3 equals cotangent of theta. Well, now I know the cotangent of theta is really the tangent of, or the cotangent is really just the reciprocal of tangent. So I know that the tangent is just going to be the reciprocal of this, so we're going to get plus or minus 3 over the square root of 7, right? If it's just the reciprocal, all we're doing is flipping it, flipping the numerator and denominator. And now, because we aren't cavemen, we simplify. So then tangent of theta equals plus or minus 3 times the square root of 7 all over 7. And that is our answer. Technically, 2 different answers. All right. For our third example, we have simplify sine x plus sine x times cotangent squared of x. And I'm going to be honest here, there is no cookie cutter method to solve these, right? Or to simplify these. This really just takes instinct or just messing around with stuff. So sometimes when I see tangent or cotangent, I'm thinking of writing it in sine or like in terms of sine and cosine, because we know tangent is sine over cosine. We know cotangent is cosine over sine. And you could play around with putting cosine squared over sine squared here. I know it's not going to work out, so I'm not going to waste my time with it, right? But my point is that you can spend time working things, and if you're not getting something nicer, then maybe it's time to change course. So another thing I see is that these both have a sine of x. One math instinct I have is to factor things, right? So let me factor out a sine of x, and then I'm going to get 1 plus cotangent squared of x. Well, this looks really familiar, 1 plus cotangent squared of x. That looks like 1 plus cotangent squared of x, or 1 plus cotangent squared of theta, equals cosecant of theta. So right here, this is really an identity, and we can replace that with, this is supposed to be times cosecant squared of x, right? Because we have this identity. So we've just substituted cosecant squared in for 1 plus cotangent squared because we have that identity. And now we can go further. We know that cosecant is really 1 over sine. So we have 1 over sine squared because we had cosecant squared. And then 1 sine here is going to cancel with a sine here. And we're going to be left with 1 over sine of x, which we know is the cosecant of x. So really, all of this junk here all simplifies down to just be the cosecant of x, which is much simpler, right? So again, no cookie cutter method, just do stuff until something starts working. For this last one, we have a word problem. Many sunglasses have polarized lenses that reduce the intensity of light. When unpolarized light passes through a polarized lens, the intensity of the light is cut in half. If the light then passes through another polarized lens at an angle of theta to the first, the intensity of the light is again diminished. So we have this red axis that corresponds with the axis of the polarized lens here, and then we have this blue one that corresponds with the second one and the angle in between them, right? So the intensity of the emerging light can be found by using the formula law, where blah blah blah, where I naught is the intensity of light coming through the second polarized lens, I is the intensity of the emerging light, and theta is the angle between the axes of polarization. Simplify this expression and determine the intensity of light from a polarized lens. So first, I guess I'm going to simplify. So I'll do the simplifying in green. So we have I equals I naught minus I naught all over cosecant squared theta. Again, if I see cosecant, I immediately kind of want to put it as sine, especially if it's already in the bottom. So 1 over cosecant squared theta is really just going to be sine over what's left, which is just 1, right? So really we just have sine squared of theta, right? Because sine is 1 over cosecant, so sine squared is going to be 1 over cosecant squared. So really we're going to have minus I naught times sine squared theta. Okay, and now we can take out an I naught, right? We have I equals I naught, factor out an I naught, and then we get 1 minus sine squared theta. Well, now this is another identity, and we might not recognize it straight up, but it's something we should certainly get used to doing. Look at sine squared plus cosine squared theta equals 1. If I subtract this sine squared over, I'm going to get cosine squared equals 1 minus sine squared of theta, right? So sometimes it's about recognizing what we can use. So really what can go in here is I naught times cosine squared of theta, because we have the identity that cosine squared of theta equals 1 minus sine squared of theta. And that came from our original Pythagorean one. I just subtracted cosine squared. So if you see a 1 and a sine or a cosine squared, odds are you can use this identity. This one is a very popular one, right? So that looks about as simplified as we can go. Cosine squared isn't going to change into anything else unless we put it back into 1 minus sine squared, but cosine squared is simpler. So, and then determine the intensity of light from a polarized lens when its axis is at a 30-degree angle to the original. So now let's do, we're at a 30-degree angle now. We're going to do the second part. So we're going to have I equals I naught times cosine squared of 30 degrees. And again, here's this lesson again, where really what this is saying is we have times cosine of 30 degrees squared. And I know that cosine of 30 degrees is square root 3 all over 2 squared. And if you don't have that memorized, that's totally fine. Again, you could just use a 30, 60, 90, punch it in your calculator, whatever works. I prefer a 30, 60, 90, because then if you ever end up doing anything with math later on when you're not allowed to use a calculator, this would be required, right? And then we have I equals I naught times square root 3 squared is just going to be 3, and then 2 squared is 4. So maybe to write this nicer, we'd have 3/4 times I naught. And that is solved. We don't get anything for I naught. What this is telling us is that the light has 3/4 of the intensity it had before passing through the second polarizing lens. If we were to read this in terms of I and I naught, so I naught is the intensity, right? So it has 3/4 of the intensity, is what it's saying. And that should wrap up 7.1. This section / chapter really just takes a lot of intuition, and I think it's kind of rocky at first until you get used to it. But once you start getting used to using these identities on your own, you just get better at it and faster. So it might feel a little overwhelming right now, like, hey, what's happening? But don't worry. I'm telling you that once you get going and you get a little used to using them, they turn out to be a lot better.